Well, in this module, I'll show you how to solve ordinary differential equations using Matlab. So let's get started. To create a new script file, you can go to New and Script file, or you can use Live Script. I'll use Live Script for this tutorial. Or if you have an existing file, if you have an open file, you can add a new file by clicking this plus sign like this. Okay, once you have a new text file, a script file, you can see the highlighting. The line is highlighted. That shows that you can add code here. You can also add text here if you switch to the text mode. If you just press this text here, you can see that there is no more highlighting now, and you can type any text here. For example, this is the first order differential equation. I'm going to type first order differential equations. So you can set this as heading of your section by choosing style here and setting it to first order differential equations. Okay, so you can see that we are still in the text mode, and I can just press enter, and I can introduce here to the first order differential equation. I'll write one for reference. So I'll just type in dy over dt equals to sum minus a by some forcing function g. Alright, so that's the general first order differential equation. Okay, now I'll start writing my code from here on. So I'll just press enter, and now I'll enter into the code mode. So I'll just press this code, and now you can see that again we are in that highlighted mode. So I'll just type in these variables that I'm going to use. For example, I'll define symbol syms, and I'll list all the symbols that I'm going to use. For example, y of t, the function, the growth rate, and then I'll use a let's say a constant forcing function. Let me call it v. And now I'm going to write the differential equation, the one I have written here. I'll write this particular differential equation here. So the syntax is, let me call it an equation, the eqn. This is how I'm defining this differential equation, and diff y with respect to t, the derivative of y with respect to t is equals to some, okay, here I'm going to use double equal to, okay, because this is part of the differential equation. The single equal is here. That means that we are calling this whole equation, this whole differential equation, we are calling it eqn. So here I'm going to use double equal minus a, that's the syntax, and static y, and I'm going to put, instead of this forcing function g of t, I'm going to put that b. Okay, so that's my differential equation, and to solve this differential equation, I'll call the solution some, we call it s1, and equals to dsolve. That's the function to solve a differential equation. So dsolve, and here the input argument is the equation. Okay, and you can also see that pop-up options that dsolve. The first input argument is the equation, and the second input argument is the initial condition, and then the other options. So I'm done with the coding, and now I can run this program. I'll use this run option, and yeah, here's the solution. Okay, the symbolic solution, because a, v, and y of t, they are all symbols. No numeric values has been no numeric value has been assigned to any of them. So that's the symbolic way of solving the differential equation. Now if I need to use the initial condition, if I want to get rid of this c1, this unknown constant, then I need to use an initial condition. Okay, so I can also use that, and let me call that condition equals to, say, somehow, let me define another variable. We call it g. Yeah, oh sorry, g was already there. Let me call it something else, maybe a capital P will work. So let the initial condition is equals to y at 0 equals to p. Okay, so once I have defined the initial condition, I can put in the second argument here, the condition. Okay, you can name it anything, like condition, C-O-N-C. You can name it anything, anything you like. It's just a variable. Okay, so now you can see that the solution is in term of this initial condition, that is P. So that's how we can solve our differential equation, first order differential equation, using Matlab. This is the symbolic toolbox. And now let me give you another example that involves some numeric coefficients, like numeric values. And let me first type in what is the equation I'm going to solve. So first I'll go to insert and equation, and the differential equation that I want to solve is dy over dt equals to d by dt equals to negative 5y plus 20. Okay, this is a differential equation that I want to solve. So for that, I'll go to again the code mode. Okay, I'll insert code, and in code I'll go to, again I'll define syms y of t, although I have already did in the upper section. And then the new equation, and let me call it equation 1, because I have already defined eqn above. So equals to, again, diff y comma t, that is equals to minus 5 static y plus 20. So this is my differential equation, and the initial condition that I'm going to use is y, the function y at 0 equals to 1. So that's the initial condition that I'm going to use. And once I'm done, I can use the, let me call it S2, because I have used this one above to make it different from that. So S2 equals to d solve. Again, the key function is d solve. So I will use d solve, and the equation that I'm going to solve is eqn1, and the condition that I'm going to use is condition. Okay, I need to change the condition to condition 1. Okay, so Now I'm ready to run this program. Okay, before that, let me save this program, and I have ODE solution. So I'll name it just ODE solve and just save it, and now I can run it again. Okay, so now you can see the solution here. The solution to the first differential equation is here, that is named as the variable is s1, and for the second case we have the coefficient -5 and the forcing function is 20. So we can see here the solution, that is s2 equals to 4 minus 3 e to the negative 5t. So that's how we can solve first order differential equation. Now please notice that you cannot use the plot function here, because the function plot is for plotting arrays. You have two arrays, and you can plot them one versus another. But here you have symbolic, the equation s2. S2. You can see that it's a symbolic equation, and plot doesn't support symbolic equations. So let me give you an example. Even if I type S2 and I'll just run it again, and you can see that data must be numeric. Okay, so to solve to plot the symbolic equation, you can use fplot. This is different than plot, but it supports the symbolic equation. That's for the symbolic equations. So now you can run this program, and you can see the response here, the plot here. But the thing is, the domain it has selected is from -5 to some +5. That's the automatic. It has automatically selected. To further refine this range, for example, we want it to start from 0. We want the response to start from 0 up to some, let's say, 2 seconds. So the second input argument is about the interval. Starting is 0 and the ending time is 2, so that we can get rid of this negative time part. Now I'll run again, and now it looks more like a solution that approaches this steady state solution 4, and because of this exponential part we have this rising star. Okay, so that's how we can solve. Even you can label the x and the y, so you can use x label. X label is time, and the y label is just y. Just type in your string. Alright, so that's how you solve the first order differential equation. Okay, now you can see the labels here, the t and the y. Okay, now from here on, let's solve a second order differential equation. What's going to change if we want to solve a second order differential equation? Let me get back to the text mode, and I'll just use another section, a different section. So I'll go to insert and section break. So it's now a different section. I can use a heading for this. It's a second order ODE with initial condition. Okay, so the let me put a second order equation, a sample second order differential equation that I want to solve. For example, y double prime plus 5y prime plus 5 by prime plus 4 equals to 1. This is my differential equation that I want to solve using Matlab. So again, I need to get to the code mode, and here again I'll start with the declaration of symbol. So I'll use syms, and let me use a different variable this time. Let me call it x of t. Okay, so x of t is my variable, the function that I want to find out of this differential equation, and that means by this x I mean that I want to solve this equation. Instead of y, I'm going to use x. Oops, I missed an x here. So that this is the differential equation that I want to solve. So again, I'll just type in equation 3, equation 2 in fact, equation 2, that is equals to diff and x comma t, and then we have we need to declare here the order of the derivative. So here I'm going to put 2 because I want to represent a double derivative, a second order derivative, plus 5 static, and again I'm going to use the diff function and x comma t comma 1. Okay, that represents the first derivative. Then the 4 times x, this is equal to 1. So this is my differential equation, and you can see the difference between the definition. All you need to do is to declare the order of the derivative in the diff function. So now I have defined my differential equation. Similarly, in the second order differential equation, we need to declare the initial condition, but we know that instead of 1 we need to declare 2 initial conditions. So let me call condition 1 is x at 0 equals to some value like that. Let's set it to 0, and then we have the second condition, condition 2, and okay, here we need the derivative. The second initial condition should be the derivative of x at 0. So for that I want to declare, let me call it a dx, the derivative of x. I want to represent with this. This is the derivative of x. So here I'm going to use dx at 0 is equals to that's the second condition. So I can put a 0 or a 1, whatever is the condition, and now I can combine both into an array, and I can call it condition 1 comma condition 2. So I'll put both of them into an array. Okay, so now we are good to go, because we can solve using the dsolve function, and the dsolve function we use a variable, we use a to assign output to, and then use the dsolve function. The input arguments, the first input argument is the equation. So here's the equation 3, equation 2, and we have the set of initial condition. We put both the initial condition 1 and condition 2 into this variable, into this array called, it would be better to name it something different, like condition 3. So I'll just put condition 3 here. So So I can now run this program. Okay, so here's S3, the solution to the non-homogeneous second order differential equation. This is our differential equation, and here you can see on the right side you can see the solution to this equation. And just like we did above, you can also plot the response using fplot, using S3, and declaring here the operating the time 0 to, let's say, 2. Right now, here's something I want to clarify, that every time you press this run option, this run button, the whole program begin to execute from the start till the end. So if you are not interested in what's happening in this section, and only want to only you made changes in this particular section and want to re-execute only this section, then you can use this option, run section, and it will save your time. Alright, so now this is your response, because we have both the initial condition and we have set that to 0, so it's starting from 0 and going towards some equilibrium solution. You can increase this time. You can, alright, so you can see that there is a equilibrium solution somewhere around 0.25. Okay, that's evident that if you substitute 0 for the double derivative and this x prime and x double prime, you set them to 0, then the equilibrium solution, that is that is x equals to 1/4. So you can also see from this picture. So you can correlate your knowledge of differential equation with the response. Is it right or not? Alright, so if you want to see the behavior, if you want to observe the behavior of a particular coefficient, the effect of a particular coefficient on your response, here's an interesting thing you can do. You can, for example, choose, let me want to see the impact of this forcing function that we have set here to 1. We want to see its impact on the response if we change this value. So I'll just go to the numeric slider, and it will introduce a numeric slider here. So now you can change this slider, you can use this slider to change the value of this forcing function. For example, I can move it to the right, and you can see that the equilibrium solution is changing. Every time you change the value, the program is re-executed. You see, it's re-executed and gives you the updated solution as well as the updated plot. So you can play with that to see how things are happening here in the equation. Okay, so now I'll jump to the system of differential equations. We have discussed the first order differential equation, then the second order differential equation, and the next step is we'll see how we can solve the system of differential equations. So again, I'll put a new section here. I'll just go to insert and a new section, and this time I'm going to solve a system of differential equation. And here is the example that I'm going to the equation that I'm going to solve. Right, the dy over dt of u and v, given they are in a vector form, and the coefficient here is in the matrix form, and then we have on the right side we have the u and v. U and v are the unknown here. So from here on, I'll just script my code. I'll script my code here. back to editor and into the code mode. Okay, so the symbols that I'm going to use here will be U of t and v of t. These are the functions that we are going to find, and now we have two differential equations here. The first differential equation, let me call it ODE1. The first differential equation is diff of u, derivative of u, and this is equal to 3 times u plus 4 times v. This is the first equation. According to this matrix notation, the first equation is the derivative of u is equals to 3 times u plus 4 times v. Similarly, we can using the second row of the matrix notation, you can use this ODE2 equals to again the derivative of v, this time the derivative of v, which is equals minus 4 times u and plus 3 times v. So these are the two differential equations. These are the that make up this system of differential equation, and combining these two, we have ODE1, then the semicolon, and then we have the ODE2. Okay, so they are in the vector form now. These are the two equations, ODE1 and ODE2. Again, we need two initial conditions, one for u and one for v. So again, condition 1, maybe I can call it condition u equals to u at 0 equals 0, and then the second condition is for v, condition v equals to v at 0 equal 1. Alright, so now I can combine these two conditions into a vector of condition 1, condition u, and condition semicolon, and condition v. Okay, so it's now again it's also in the vector form, and now I can use the dsolve function, but this time I expect two functions out of the dsolve function, two output argument. One is the u, and the other function that I want is the v of t. Okay, and dsolve, I can use the function dsolve ODEs comma conditions. Okay, so now we have two differential equations and with two initial conditions, so we'll get two outputs. Okay, we'll get two functions out of this, so we'll get two equation, one for u and one for v in the solution. Okay, so as you can see, we have u of t equals to sine 4t e to the 3t, and then we have v of t, that is cos 4 of 4t times e to the 3t. So that's how we can solve a system of differential equation using this Matlab symbolic tool. Okay, now, and you can plot each of them again using fplot function. Using fplot, you can plot u. Let's see, you want to plot u of t, you can plot it here. and again I'll just run section. Instead of running the whole program, I'll just run section. So here's the solution, but again it's from -5, so I'll just set the range from 0 to say 10 and run this program. Alright, so you can see the instability there because of the e to the 3t, that's the growing exponential. Since the eigenvalue is positive, so the system is unstable, and you can see that it's blowing up. Alright, so the next thing I want to show you is the solution using the Laplace transform. We can also solve a differential equation using Laplace transform. So in the next I'll create another section, and here we'll discuss how to use Laplace transform. Okay, so here's the equation for Laplace transform that we use. We have a function, and that function is multiplied with this kernel function e to the minus st. We integrate from 0 to infinity, and we get the resulting function is in s domain instead of a t domain. Okay, so first let me show you how to apply Laplace transform to some of functions, some of common functions like exponential sine function. Let's see, we have let's define first the variable. Let me define some variables: a, t, s, w, r, and l. These are some of the variables that I'm going to use. So the first function that I want to find Laplace of is exponential of minus a times t. This is the function I want to find the exponential, the Laplace transform. So it's straight away. You can just type Laplace of function f. Okay, so I'll just run this section, only this section, run section, and here's the, so since I haven't assigned to any variable, let me call it some Laplace of exponential le. So now instead of a and s, the default answer variable, it has been assigned to le. Similarly, if I have another function, we call it vs, I can also directly use the function inside the Laplace input argument, like Laplace of sine, instead of omega I'm going to use w, and I'll run it again. So here you can see the Laplace of sine function here. Alright, so that's how you can find the Laplace of a signal, Laplace transform of a signal. Our interest here is, we are more interested here in the role of Laplace transform in solving a differential equation. So let me give you an example that we have, for example, we have an RL circuit. So the differential equation of an RL circuit is like this: the di over dt times R over L R over L, and we have on the right side we have Vs over L. This is supply voltage. That's V representing supply voltage. Okay, so this is the differential equation for an RL circuit. And like for the impulse input, if we have an impulse input, then the Laplace transform gives you this transfer function. Using Laplace transform, we can get this transfer function. Just replace the derivative with s times I of s, and here you'll get I of s. On the right, if you have a delta input, so here you'll get a 1. So just combine those terms, and you'll get this transfer function. So once you have the transfer function, you can proceed to find the solution. For example, I have the numerator in this h of s. In this h of s, I have the numerator as 1 over L, and in the denominator of this, I'm going to use a different variable. Din underscore h is some s plus R over L. So these are the numerator and denominator of the transfer function of the impulse response, Laplace transform of the impulse response. So what is the system equation here? The RL equation is the RL impulse, the RL transfer function h of s becomes the numerator underscore h over the denominator underscore h. That's our transfer function of the impulse response. And you can also let me just run it here to show you instead of. Okay, here you can see that 1 over L into s plus R over L. This is the transfer function h of s we have produced here using the symbolic math. And if you want to find the solution, you can use the inverse Laplace here. I Laplace is for the inverse Laplace of sys underscore RL. Okay, and I can run this section now. So here it is. This shows you the impulse response of the RL circuit. So let me repeat the steps one more time. This was just for demonstration. I'll just get rid of this guy. We have an RL circuit, and this is the transfer function if we are using an impulse input. Okay, means in other words, this is the Laplace transform of the impulse response. Transfer function represents the Laplace transform of impulse response. So we just scripted the numerator here, the denominator here in this second line, and then using the numerator over denominator gives us this h of s. This is the, in fact I can just call it h to make it more consistent. So I'll just call it h, and then using the inverse Laplace of h gives us the impulse response. Okay, this is the impulse response. So now we know that if we have the transfer function of impulse, if we have the Laplace transform of impulse response, we can find solution for any input. For example, here we have the Laplace transform of sinusoidal input, and we can move one step ahead, we call it sys underscore RL, we can use it now, equals to the h function times the transfer function of the forcing function. So in this new case, I'm going to use the sinusoid as the forcing function. I'm going to find the solution when the forcing function is sinusoid. So I'll just multiply the Laplace of this sinusoidal forcing function, and then all I need to do is to take the impulse, the inverse Laplace of sinusoidal RL. This will give us the solution if the input to the RL circuit is a sinusoidal signal, sinusoidal input. So I'll just run this section again, and here is the solution that is given here on the right as yt. Okay, so this is our solution to differential equation. Differential equation is here, where v of t, the forcing function, is a sinusoidal signal. Okay, so you can try other things like you can use exponential minus, let's say, minus a static t. You can use this forcing function, and the rest of stuff stays the same. Okay, and here's the new system transfer function is here after you change your forcing function to exponential, and here's the solution of the system. This is solution of the RL circuit when your input is in exponential instead of sinusoid. So you can change the forcing function in this line, and you can find response to an RL circuit quite easily. So that's the way you can solve your system using Laplace transform. Okay, so now I'll show you one more thing here. That's to find some graphical responses, some graphical representation of your differential equation. That's quite handy in many situations. You don't need to explicitly solve in several cases. You don't need to explicitly solve your equation, but to see either the impulse response or the step response. So the next step I'm going to do is to find the step response, and I'll take this I'll take the RL circuit as again my example. My example is still be there, that RL circuit, and let me set it as heading step response, and the equation is going to be, the equation under consideration is this RL circuit. Let me produce it here one more time. Okay, in order to see the step response, you cannot use the symbolic variables like L and R. You need to declare some values, some numeric values. Okay, so for that, let me declare that L is 100 micro. Okay, well, what I'm doing here is, this is in the text mode, I need to be in the code mode. So it's L equals to 100 micro and R equals to 0.2. So I'll use these values, and now I'm going to declare a transfer function here. So to declare a transfer function, to define a transfer function, I'll use the function TF. Okay, the function TF, the syntax of the function TF is, let me say, system equals to The function TF is we need to put the coefficient of the numerator and all the coefficients of the denominator. These are the two vectors that we need. So how to define the variables in the coefficients in the numerator? We type in numerator. The only term here is 1 over L. Okay, since I have defined L here, so it will assign the value of L. So 1 over L you will get a numeric value, it's not symbolic anymore. Similarly, DEN is here we need S plus R over L. Okay, in the denominator there is S plus R over L. So for S, instead of S, I'll just type in 1 and space. Then for R over L, second is R over L. So starting from left to right, that represents the highest coefficient. For example, if you have S square plus 2S, then you'll type in 2. This is to show you. You'll type in here 2. I can just run this equation. Yeah, you can see in the numerator we have this 10,000, and the S square is the coefficient. 1 is the coefficient of S square, 2 is the coefficient of S, and R over L is the coefficient with S power 0. So you can use this order. The first represent if I put a 0 here, okay, so it means that it will detect as that there are 3 terms in the denominator. The first one will be it will call it S square, the second will be S term, and the third will be it will treat this third term as 0. Alright, so this is how you can define your numerator and denominator from a given transfer function. This is your given transfer function. You can determine the coefficients and put them in this form, and now you can use the system equals to TF, that means transfer function numerator comma denominator. Now I'm going to find the step. Here I want to find the step response. I'll just type in step, and the system here is SYS, the transfer function. I need to type in the transfer function. Okay, this is the transfer function. I'll run the section, and here is the step response of the RL circuit. Okay, if we apply a step function, this is what you are going to see. Okay, so another thing we can do here is the impulse response. You can also type impulse, and again this transfer function you are going to type in is sys. So here is the impulse step response, and at the bottom here you get your impulse response, step and impulse response. So you can use these functions, but remember that your input argument need to be a transfer function. So once you have your transfer function, you need to type in this way using numerator and denominator vectors. You can define your transfer function, and then you can use the step and impulse response. Okay, now if you want to find the response of the system to sinusoidal input, what we need to do here is let me first show you the Laplace transform of sinusoid. This is the Laplace transform of sinusoid, and for instance I get rid of these, and here's the transfer function of RL circuit. For the to script the transfer function of this sinusoid, that is omega. Let me type in a numerator. That is the in the numerator we have omega, and let me use omega as 10. Right, let me use omega equals to 10. So here I'll just type in 10, and in the denominator underscore b, I'll script, since I need to the denominator is quadratic with s square, so the first coefficient is 1, the highest coefficient is 1, and then we have the there is no s term there, so I'll put a 0, and then there is the omega square term. So instead of 10, I'll write in here 100, because to show to give the square of omega. Okay, you can just type in 10 static 10, or also you can type in 10 square. Okay, so you can type now that the transfer function of this system, this sinusoid, is TF numerator of v, numerator underscore v, comma denominator underscore v. That's the new then this is the transfer function of this sinusoid. To find the response of the RL circuit with this new forcing function, we'll multiply these two transfer functions, the cis and this v. So we'll get, let me write y equals to cis static v. Okay, this is the new transfer function that we will get by multiplying the transfer function of the sinusoid times the transfer function of the RL circuit, that is the Laplace transform of the impulse response. So we'll get this new transfer function here that gives the response that is in the response to the RL circuit to a sinusoidal input. Response of RL circuit to a sinusoidal input. So here I'm going to show you a few of the analysis you can, a few of the plots that you can create using this transfer function y. Let me first use the first one that I'm going to use is pole of y. Then this gives the poles of the transfer function, the poles of this transfer function y. So there are 3 poles of this transfer function, as you can also see from this view here. It says that two are the complex conjugate, and one is the real one. One is the real, and 2 are the complex conjugate, and this is multiplied by 1000. So it means 1 is at the minus 2000, and 2 are at the plus minus 20. In fact, you can also plot them using easy plot of y, again transaction, and here is the PZ plot. Here you can see here the poles and zeros. Here since in this transfer function we only have poles, no zeros here, so you can see those cross. Let me zoom in. You can see those cross. These represents the poles of the transfer function. So 3 poles are here. Complex conjugate are on the imaginary axis, and the only real pole is at the minus 2000. And I mentioned maybe 20, but it is at plus 10 and minus 10 the imaginary poles. Okay, that based on the omega equals to 10. Since omega equals to 10, so the poles on the imaginary axis are at plus 10 and minus 10. Those are the complex conjugate pairs. Alright, similarly you can use another way you can analyze this is using uh, the, 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 the option that you can use is the linear system analyzer. You can use this option that gives you multiple options for the analysis of your system. Let me just execute this system. Here it will open the response. Okay, it's the step response. Okay, this gives the step response, but since we have the sinusoidal input, because we have modified this transfer function, so we need to get to the impulse one. We'll get to impulse, and okay, so now this is the response of the system to the sinusoidal input. You can zoom in to get to your desired region. Okay, similarly, if you want a different kind of analysis, you can also go to the frequency domain analysis. You can see that. Okay, so with that said, I'll conclude this tutorial. In this tutorial, I showed you how to solve first order, second order differential equation, even a system of differential equation using Matlab. You can do it using symbolic math tool, symbolic tools that gives you answer, that gives you a solution um, in terms of variables, no numeric values, and you can also get your response as a plot, as a time plot. You can also get your response in that form. Similarly, I showed you how to use control sliders to to see the effect of a particular variable on the response. So that's it. I'll say bye bye.